All right. Good morning, everybody. Got it's kind of slim pickings Friday before spring break here. Senioritis kicking in strong. You guys feeling it? No? No senioritis? Yeah? You like school? You want to stick around? Yeah. You gonna go to grad school? Maybe, yeah. Anybody doing anything cool for spring break? Going somewhere? Where?
Parker, Arizona.
Parker? Okay. My mom lives right out there. She lives in Lake Havasu.
Oh, really?
Yeah.
I've never been there.
Okay.
One of my buddies has like they have like a family cabin.
Nice. With a boat and stuff?
Yeah.
Yeah. Yeah.
River house.
Water might be pretty chilly still right now, huh?
Oh, yeah.
Yeah. Very cold. Yeah.
Definitely what's-
Yeah. Yeah. Nice. Who else? Anybody else going on trips or do anything fun? Where are you going, Erica?
San Francisco,
Yosemite? Yeah. Nice. That's cool. There's a group of girls that I like nursing girls are going. Are you part of that group?
my roommate's in nursing, but it's just, I'm going up with her. It's on.
Okay, because there's a bunch of other girls that are going to Yosemite too. Okay. Are you guys camping up there? Or-
No, my roommate's from up north, so we're just going up to the house.
Oh, cool. That's awesome. Have you ever been to Yosemite?
No, I've never been to
Oh, wow.
Yeah,
Okay.
I'm saying.
Yeah, because you're from the south, right?
Mhm.
Yeah. Yosemite is incredible. It's yeah, I think it's one of the most beautiful places on earth for sure. It's amazing. Yeah, there's nothing like when you first drive in and get that view. It's ridiculous. Yeah. Who else? Anybody else going somewhere? Faith, where are you going?
I'm going to Flagstaff.
Flagstaff? Okay, that's cool. Might be some snow.
Yeah, we either want to go skiing or snowboarding.
Nice. Cool.
So that'll be fun.
Yeah, that's awesome. Yeah. Anybody else traveling? Yeah, where you going, Pete?
I'm going to my friend's house in Boise. My roommates,
Oh.
we're gonna ski in McCall.
Oh, yeah. Oh, that's a beautiful area. I've never been. but- Okay. Nice. You driving out there?
No, we're fine.
Okay,
Yeah.
that's nice. Yeah.
The flight was only $100.
Really?
Yeah, I
Dang.
mean, it's not a good airline.
Yeah.
It's
You
weird.
gotta pay to go to the bathroom, like one of those. Yeah. Yeah, those are fun. Yeah, nice. Well, should not too long of a flight probably either.
No.
Yeah, that's cool. Nice, cool. Well, we're heading to Disneyland Sunday, staying up there a few nights and then going California Adventures Monday and Disneyland on Tuesday. So that should be fun. Our big celebration. Yeah, but taking the kids out of school because they have a different spring break than us. So, yeah. But, yeah, so, they'll be fine. Yeah. They'll be fine. But yeah. So, well, cool. Well, hope you guys can get some rest and enjoy spring break for sure. Yeah. All right. Well, today we'll finish up this stuff on cardiovascular disease and diabetes, and then yeah, and then we'll come back on Monday for the gallery walks, and then Wednesday for exam 2. So, any questions about any of that? What we've got going? I just released your concept map grades. So if you, yeah, I would definitely, if you got marked down on things, then definitely make sure you figure out what those things were. I gave voice comments on all of them. I also wrote it, but I get the feedback often that in class, it's not an issue that you can't read my writing because you can ask, but on the feedback, sometimes like the feedback's worthless because we can't read his writing. So I did the voice comments too. So listen to that if you're not sure why you got marked down. Yeah, but definitely the same stuff shows up on the test too, right? And on the gallery walk. So make sure you have it down if you missed anything on that. Okay. A lot of it was just like not having the right level of depth or the right details. And so just make sure you correct whatever you missed on that for the next stuff. So, all right. Questions on any of those things or what's coming up in the class? Okay. All right. Well, we so finished up the cardiovascular disease stuff, and so now we'll dive into this other major disease of our society, which is type 2 diabetes. Okay. And when you think of type 1 diabetes, what's the primary issue or pathology with type 1 diabetes? What's the problem with it? No insulin, right? Yeah, we can't make insulin. it's a autoimmune disorder, meaning that our immune system for some reason attacks our pancreas, kills those beta cells, and we can't make insulin. Okay, my son Soren, who's 12, has type 1 diabetes. He was just diagnosed 2 years ago. And yeah, he's got the whole setup with the pump and the continuous glucose monitor. I can actually see his blood sugar on my phone at any time, which is really nice. And we'll get alerted if his blood sugar gets too low or too high, or if we can't see his blood sugar for some reason. So the technology is pretty incredible these days. It's really what's known as like the artificial pancreas now, because what your pancreas does, right, is senses glucose and then releases the right amount of insulin in response to that. And so that's what the combo of the insulin pump and the continuous glucose monitor can do now with the right algorithm. Is it's pretty much doing that. The continuous glucose monitor is always telling the pump what his blood sugar is. If it starts going too low, it shuts off all insulin release, right? If it starts going too high, it gives them more insulin. So it's like, yeah, it's considered an artificial pancreas. Yeah, not perfect yet, but those were just released. Like the FDA just approved that technology about five years ago, because insulin's a lethal drug, right? If you give somebody too much insulin, they can die pretty quickly. And so to trust a computer algorithm to dose you with insulin is a scary thing, right? So it's been in development for over 30 years, that pancreas, artificial pancreas, but its timing worked out good for us because it's definitely controls the sugar way better than it would have without it. But yeah, cool.
Yeah, so like, what about if it, like malfunction? If it gets too much insulin?
Yeah, so it has a bunch of built-in kind of things for that. Like if there's just definitely, yeah, I mean, it definitely can malfunction in a way, like if the glucose monitor is telling the pump like the wrong number, then that can mess some things up. But there are kind of built-in checks and safety checks for all of that. Like if the glucose monitor is kind of getting weird readings, it'll tell you that it's not fully confident in its readings, and it'll tell you to do a calibration with the glucometer. So there definitely are kind of multiple checkpoints along the way, I think. So, but yeah, I don't know all the details of how it works, but
Personally, if I had that, like something regulating,
yeah,
I would be a little.
totally, yeah. No, it's definitely, the crazy part was that I mean, people have had continuous glucose monitors and insulin pumps for many years. That's not a new thing. And so a lot of real tech savvy type 1 diabetics created their own algorithms to do this. And they've been doing it for the past 10, 15 years, actually. And so, and they put that programming into their insulin pumps to do it, which was kind of cool, but it's just been finally released for real. So yeah, it's pretty nice technology for sure. Yeah, but that's type 1, right? So then if type 1, the issue is no insulin, what would be the main issue you would say with type 2? Okay, too much insulin. What any other ideas? Yeah, so that's kind of the hallmark thing of type 2 is insulin resistance, which is really kind of represented here with this one, right? So decreased glucose uptake, right? And so when somebody's diagnosed with type 2 diabetes, they still have insulin production in their pancreas. It's just that the cells are not responding to that insulin like they're supposed to. And so that's known as insulin resistance. This really, in a lot of ways, is one of the primary tissues that's a problem with type 2 diabetes is the skeletal muscle, because about somewhere between 75 to 85% of our glucose disposal happens in our skeletal muscle, right? And so if we have a problem with getting glucose out of the blood, then we got a problem with our skeletal muscle, because that's where most of it happens, right? So that's one problem, and that is the one that everybody thinks of when we think of type 2 diabetes, but it's not the only pathology in type 2 diabetes. And that's why I like this slide here, because it shows two of the other primary factors as well, which number one is that our pancreas, or the pancreas of a type 2 diabetic, is not functioning properly either. And so we do have, by the time diagnosis of type 2 diabetes happens, we don't have as strong a beta cell function as we did before. Okay, so remember, beta cells are the ones in the pancreas that make the insulin. And this is kind of an unfortunate part of type 2 diabetes and how we diagnose it, because what's the diagnostic criteria for type 2 diabetes? Anybody know? Or what would we test to be able to say, all right, you have type 2 diabetes? You guys know? Alex? Yeah, fasting glucose for sure. Yeah, and so it's above 126 is the fasting glucose cutoff for type 2 diabetes. Between 100 and 126 is considered pre-diabetes, like we're looking at before, which like over a third of our country has that. So it's all based on glucose levels. We can also do it with hemoglobin A1C. There's criteria for that, but the problem with that is by the time somebody's glucose levels are higher than normal, they've had the disease for many years. Because what happens is when your body starts becoming insulin resistant, it just takes more insulin to get the same amount of glucose out of your blood into your cells, but your pancreas can do that. Your pancreas can release more insulin and kind of make up for that insulin resistance. And so there's many years where the pancreas is just overworking itself to make up for that insulin resistance. And by the time, and that actually causes damage to the pancreas. We're not exactly sure why. It's probably related to the glucose levels, maybe fat levels, maybe that visceral fat is damaging the pancreas too. It could be the pancreas is getting overworked. There's not really direct evidence for that. But anyways, by the time somebody's diagnosed with type 2 diabetes, they're down to 40% of their pancreatic function. So it's not like, all right, now all of a sudden they have a disease because their blood sugar is over 126. They've had it for years before that. And so really it's an issue with the way that we diagnose it. Because if we would just test insulin levels, like in response to a meal, then we would see hyperinsulinemia, just like much earlier than we ever see that hyperglycemia, right? And so it's just a lot harder to test for insulin in the blood. There's no point of care test for insulin because it's a protein. It's different in the way that it has to be tested. It falls apart a lot easier. So that's a big issue, right? And that's why the pre-diabetes state is a really important one to look at too, even though it's not technically diabetes yet. It's really important because that person has a disease. They're moving towards damaging lots of parts of their body, including their brain and their arteries and their heart, even when they're in that pre-diabetic state. So really important thing to think about. So again, yeah, so we have decreased beta cell function. And that means beta cells are actually, there's a lot of the beta cells that have died, as well as the beta cells that the person has left aren't producing as much insulin anymore. So now, by the time we diagnose it, we've got the cells not responding to the insulin, which is this one, right? But then we also have not as much insulin release anymore. So the pancreas isn't able to make up for that insulin resistance anymore by the time it's diagnosed. And then thirdly, this HGP stands for hepatic glucose production. Okay, so hepatic means which organ? Liver, yeah, liver for sure. So hepatic, we'll talk about the hepatic portal system in a second here too, so this is kind of supposed to look like a liver, but hepatic glucose production. So our liver is primarily responsible for controlling our blood sugar when we're not eating. Okay, so for all when we're sleeping, anytime we're fasting, we're not bringing in glucose. So there has to be, and your body uses up the little bit of glucose that's in the blood pretty quickly. So there has to be some way for us to keep adding glucose to the blood, and that's the liver's job, right? The liver is responsible for that because that liver is the number 2 place that we store glycogen. Remember, right? We talked about muscle is the number 1 place for glycogen, but then the liver is the number 2 place. The reason we have glycogen in the liver is so the liver can release glucose when we're not eating, and so to maintain our blood sugar levels. The way it's supposed to work is if we're not eating for a long time, our liver is slowly pumping some glucose into our blood to maintain our blood sugar. If we go ahead and eat, then that causes an insulin spike, right? Because that's going to cause our glucose to go up because of what we just ate. Our insulin goes up in response to that. Insulin's supposed to go to the liver until the liver stops releasing glucose. We got plenty here because we just ate, right? But that mechanism is broken in type 2 diabetics as well. So that the liver responding to insulin and stopping its release of glucose is not working either. So instead of instead of when you eat, your liver stops, normally your liver stops releasing glucose. Instead, it keeps releasing it, and sometimes it even releases more. So that contributes to the hyperglycemia that we see in type 2 diabetics as well. So that's a big factor. And this is directly connected to visceral fat, right? It's that fat around the organs. And one of our biggest depots of visceral fat in the body, just the place that it tends to collect, is right next to the portal vein. Okay, and so the portal vein is the vein that's getting all of our blood, that we just picked up all the nutrients from our intestines, and then it goes into the portal vein and then goes directly to the liver to drop off all those nutrients, because the liver is responsible for processing most of our nutrients, right? And so all that blood is getting dumped to the liver, but there's a big depot of fat, visceral fat, right next to the portal vein. And visceral fat is highly active, so meaning that it's constantly breaking down triglycerides and releasing those things into the blood. And so because of its proximity to that, the portal vein's proximity to the liver, and that visceral fat depot right next to the portal vein, it's constantly, the liver is just constantly receiving a lot of extra fat when you have a large fat, a high amount of visceral fat. And so that ends up causing a buildup of fat in the liver, which is known as fatty liver disease, right? And that can cause all of this damage that we're talking about in the liver, being resistant to insulin and releasing too much glucose. And it causes other problems as well, like eventually, potentially liver failure and things like that. But it's definitely directly connected to type 2 diabetes, is these liver problems. So, yeah. And physical inactivity and obesity are directly connected to all three of these factors. And we'll talk a little bit more about that. But questions on those three kind of components to the pathophysiology of type 2 diabetes? Yeah, so type 1 is a pretty simple disease compared to this, right? This one is multifactorial. There's definitely genetic components to it, but there's many lifestyle factors to it as well. So even if you've got all the genes that would move you towards type 2 diabetes, there's still a chance of you not getting it if you eat right and you exercise. Type 1 diabetes, I mean, there's really, we don't really know of a good way to prevent it. I forgot Betsy was back there. It's like, what's that animal running here? Yeah, so I bet you. Yeah, so that this disease is much more complicated really than type 1 diabetes is. So, all right, questions on that at all? Okay. All right. So let's talk a little bit about some of the related factors here. So back to this idea of visceral adipose tissue or visceral fat. Kind of the main theory around why people build up visceral adipose tissue has to do with this. This is really just energy balance, right? So if our energy intake is higher than our energy expenditure, then we get a positive energy balance, right? And our bodies are so stinking good at holding on to calories that we're not going to get rid of those calories, right? And that's part of the problem probably with our genetics, is that our genes are supposedly the same genes that our ancestors had, that were hunter-gatherer type societies where they went through periods of feast and famine commonly, right? So they would be almost starving, just eating roots and things like that for weeks at a time. And then all of a sudden they would kill a buffalo or something, right? And then they would just have this giant feast, let's eat it all. And they ate it all too, right? They ate all the fat, all the bones, they ate everything, right? Because it was all important nutrients. And so the genetics for them made perfect sense to not waste a single calorie of that, right? Because in a couple of weeks, they're going to be starving again, right? And so that's what happened. That's what the genetics are set up that way, to store every bit of energy that comes into our bodies, right? Because there's another famine coming, right? But we're always in feast mode now, right? We got the same genetics, and it hasn't really changed. So we're always in that feasting time, and so we're still holding on to every single calorie that comes into our bodies. And so we have, even when we fill up our subcutaneous fat, which is really what this is saying, we can saturate our subcutaneous adipose tissue, right, our fat underneath our skin. Even when that gets filled up, the body's got other ways to hold on to calories, right? Which is visceral fat. Okay, so then we start building up fat around our organs like this, in our organs, right? In our liver, in our heart, in our muscle, in our kidneys, in our pancreas. And there's negative consequences to all of this. And you can see all of this leads in each of these organs, it leads to insulin resistance and inflammation. And then we already talked about the impaired insulin secretion when we get this, and this is known as lipotoxicity. So it's just like the toxic effects of building up bad types of fat in our organs. We can also have, with type 2 diabetes, we also have glucotoxicity. And that's just, we talked about that a little bit already with eNOS, kind of with getting glucose stuck to that enzyme and damaging it a little bit. That happens to it happens to our neurons as well. So if you're choosing this one for your final project and you want to get into some more information on the pathophysiology of these, those would be some good terms to Google, like the lipotoxicity of the liver, or glucotoxicity of the pancreas, or something like that. And there's some newer information on that outside of what I've talked about in class. Yeah, so that's pretty much the portal, and this is all known as the portal vein theory, which is here, the portal theory. Again, we've got all this visceral fat. It's right next to the big portal vein, which dumps into the liver, and then that causes the liver to build up fat. Okay, now there are good types of fats that we can store in our muscle too. So all fat buildup in the muscle isn't a bad thing. Endurance athletes tend to have a good storage of fat in their skeletal muscle, but it's actually different types. There's like, I don't know all the types that well, but there's like ceramides versus different types of fats, and there's bad ones that build up in disease states, but then good ones that build up in endurance athletes, and that gives them access to that fuel, right, that they need during exercise. But yeah, different types of fat buildup. Okay, questions around any of that? Okay, and I kind of already said this one, but again, maybe a new vital sign and a new really important thing to look at is just a simple measurement of waist circumference, because even though that doesn't give you a perfect measurement of visceral fat, it's correlated quite well with visceral fat. The larger waist circumference, the more visceral fat the person has, and so that's why that is a much better predictor of health than total body fat or other things looking at different distributions of fat, because this shows a little bit more about what's going on in the visceral compartment. Yeah. Okay. So then this is just a slide. You don't need to know the full mechanism of the insulin response, but this is kind of what's going on here. So when we have insulin, which that's the protein insulin there, binds to an insulin receptor, which is right here, we have this whole series of events here. Okay. And a lot of this is because different proteins get phosphorylated, right? An ATP comes next to it and puts a phosphate on it, and that changes the protein in such a way, causes all kinds of things downstream. One of the things that causes is right here, which is GLUT4 translocation. We kind of talked about that one already. It's that protein that goes to the surface of the cell, lets glucose in, right? That's what we think of when we think of insulin, because that's its main role, is to just open up that gate for insulin or for glucose. But then it's also little less known of insulin's role, but it's also a vasodilator. Insulin actually activates eNOS, just like that mechanical shear stress does that we talked about, right? And it's supposed to lead to nitric oxide production and vasodilation. And all of this working properly leads to a more healthy endothelial function, right? So the reason I have this slide is just kind of showing this very direct connection between type 2 diabetes and cardiovascular disease. So we see when we have a problematic insulin receptor, problematic insulin mechanism, which we'd see in type 2 diabetes, we have all kinds of things. So there's one of those fats I was talking about that can mess with things, ceramide, diacylglycerol is another one. But pretty much every step along this insulin pathway can be messed up in a type 2 diabetic. And so instead of activating eNOS, we actually downregulate eNOS, which decreases our nitric oxide, which leads to endothelial dysfunction. And so we just kind of have this direct connection between these two diseases. People with type 2 diabetes are something like 100% more likely to get cardiovascular disease than people without it. So it's just these two diseases go hand in hand for sure. Okay, questions on any of that? Okay, so that's a little bit of the pathophys of each of them. Now let's talk about the effects of exercise. right? So one thing about this, similar to how we talked about with blood pressure, insulin resistance, or at least insulin or glucose uptake, we can have an acute effect of one bout of exercise as well as a chronic effect. So first of all, we've got the acute effect here. Again, like I said, somewhere 85-ish% of our glucose disposal happens in our muscle. So if we've got an impairment there, if we have type 2 diabetes, then we have a problem with our skeletal muscle. Okay, so exercise both acutely and chronically increases the amount of GLUT4 that we find inside of muscle cells. Okay, just a single bout of exercise can increase GLUT4 on our cells for 3 days. So this is why exercise is such a drastically important thing for type 2 diabetics. And I love this stat because it's like, yeah, most people, when you tell them, all right, you got to exercise 300 minutes a week, you got to exercise, 5 days a week, whatever it is. Most people that don't exercise just kind of think, yeah, that's not happening, right? But one bout of exercise helps them for 3 days, right? So that gives them lower blood glucose for the next 3 days, right? So one bout is better than nothing, right? And 2 bouts is even better than that, right? But this is just a real hopeful thing. I feel like for type 2 diabetics is just doing 1 bout is very helpful for you. And this is all mediated by 2 primary cellular mechanisms, which are shown here. And this little figure right here is from this article. And this article I have for you on Canvas. So on Canvas in the top module, it's like the course overview or start here module. At the bottom, there's a little folder there that says like type 2 diabetes articles. And there's another one that says atherosclerosis articles. You can hop in there when you start working on this paper. And I've given you a few articles to get you started on the pathophysiology mostly, and then on the effects of exercise. So this image is from one of those articles there. So as part of that final project, you can use those articles, but then you're supposed to find 3 peer-reviewed articles on your own to use that aren't from that group. And then what I really want out of those articles is for those to add information that you didn't already have from class, right? So if you just, on your concept map and on your paper, you just give me everything that I gave you in class, that's fine. That's not going to get you an A, okay? But if you want to have there's a whole section on the rubric for like new information that came from the articles that you found. And so you'll definitely get a lower score. But so to get a good grade on this one, you'll need to find some articles that add new information that I didn't already give you in class, okay? Or that aren't from those articles that I gave you. So again, we got a while till that's due, but just kind of be thinking about that. Okay, so that article is really good with outlining these mechanisms. So this is a skeletal muscle cell here. We see the insulin receptor over here. That insulin receptor, when it gets activated, leads to GLUT4 coming to the surface of the cell. But then we have this whole non-insulin dependent mechanism for doing the same thing. And again, and this explains this part right here. This explains this acute factor. So one of the mechanisms is ATP, right? We know that's got 3 phosphates on it. We break that down into ADP, that's got 2 phosphates. When we're really exercising hard, we actually break down that ADP as well into AMP, so there's just 1 phosphate left. And so this ratio of AMP to ATP is kind of like almost like a fuel gauge for your cells, right? So the higher that ratio goes, the more the cells know we're running out of energy, right? Because we're running out of ATP and getting more of this broken down version of ATP, AMP. So really what happens, this is one of the main mechanisms for increasing GLUT4 in skeletal muscle cells. When that ratio of AMP to ATP starts going up, that activates some other proteins in here, which eventually causes GLUT4 to go to the surface, right? So that makes perfect sense why exercise does that, because we're using a lot of ATP, right? And then secondly, we have many, many proteins inside of our cells they're in part of the calmodulin family, which just means that calcium modulates them, right? Calcium changes them in some way. Troponin is one of those, right? But we have this whole group of calmodulins inside of our skeletal muscle that when calcium binds to it, it changes some other proteins and then causes GLUT4 to go to the surface of the cell, right? So again, we know when we start exercising, we start dumping calcium into our cells. Some of that goes and binds to troponin. Some of that other calcium goes and binds to these other calmodulin proteins that cause GLUT4 to come to the surface of the cell. right? So we got two like direct ways that exercise leads to GLUT4 translocation without the help of insulin at all. We don't need insulin to do this at all, right? So this kind of bypasses that broken mechanism in type 2 diabetics and uses a totally different mechanism. Okay, questions on that one? So that would be the acute part, okay? And so if you're doing this one on the concept map, you do need to outline, here's the acute effects of exercise on insulin sensitivity or on glucose uptake, and here's the chronic one, okay? So chronic effects here. Again, it's modulated by those two same things, so that makes it easy. You don't have to learn a new mechanism. It's AMP kinase and calmodulin again, okay? And so we can see that again, here's calcium, here's the AMP ATP ratio. The key factor here is this guy right here, PGC1 alpha, okay? PGC1 alpha is the primary regulator of mitochondrial health in our cells, right? So if we can somehow turn on PGC1 alpha, then then our mitochondria are gonna grow. They're gonna get more mitochondrial enzymes, they're gonna get bigger mitochondria. And so that's what happens. So both those mechanisms do that. Both the AMPK and the calmodulin ones do that. And so then we get three primary effects by turning on PGC1 alpha. Well, the first one is not by turning on PGC1 alpha. It's just not only does exercise turn on sending GLUT4 to the surface, but it also makes our cell make more GLUT4. So it's ready for next time. But then these other two, mitochondrial biogenesis and fiber type transformation. Okay, so our muscle cells start moving from type 2A to type 1 fibers, as well as type 2X over to type 2A fibers. So they become more oxidative, right? We add more mitochondria to those, right? And so then the more oxidative a muscle cell or a muscle is, then the more blood we have to send to that cell, right? And then the more glucose we dispose out of the blood there, because we're getting more blood to active tissue, right? And so that's how that helps lower our blood sugar. Okay, so we expect to see somewhere around a 25% improvement in this kind of marker of insulin sensitivity with somebody who's trained for a couple months of aerobic training. Okay, so some of the studies here. This was part of my dissertation work as well. That same study we talked about before. We didn't just measure their artery function. We also had continuous glucose monitors on them, and we measured their 24-hour glucose before they started the training study, and then after the 8 weeks of training. And it was kind of inspired by some of these studies. This study back in 2011, they took type 2 diabetics. They just had them do one bout of HIIT. Right? These are people that weren't exercising, had type 2 diabetes. They had them come in 2 separate days. One day they just had them come in, put a glucose monitor on them, said, all right, go home, and then we'll see you tomorrow, and measured their glucose. And then another time had them come in, had them do a high intensity interval training bout, the same as I did, the 10 by 1, and then put the glucose monitor on them and said, go home, we'll see you tomorrow. Right? And so here's the difference in their glucose values over that 24-hour period. Right, so the pre-HIIT would be the day they didn't do any exercise, and then the post-HIIT. So this is breakfast right here, right? That's why you see a spike. This is lunch. This is dinner, and so you can see that much higher glucose values when they didn't do the exercise, much lower when they did. All right, this is kind of their average glucose going down. And then they also took muscle biopsy. Well, they continued this study and did a 2-week training part of this study too. So it wasn't just the acute bout, but they had them train for 2 weeks, which was only 6 sessions of HIIT, three sessions a week. And they did a muscle biopsy with these subjects. So muscle biopsy before and after, and that's how you measure GLUT4, right? So they're measuring how much of that GLUT4 protein's inside their skeletal muscle. This was a ridiculous finding, 369% more GLUT4 after just 6 exercise sessions. That was it, 6 times in that. And so there's just something incredibly powerful about high intensity interval training and just activating your cells to make more GLUT4 and to dispose of glucose. Right now, they didn't have a control group, so we don't know what would have happened if there was another group that did continuous exercise for 6 sessions. Maybe it would have been the same. We don't know, because it wasn't a controlled study. Just the HIIT group. So, okay, questions on that one? Okay, so then that's the effects on the skeletal muscle. Then let's talk about the other factor, effects on the liver. Okay, we've already kind of talked about this visceral fat idea. We know that exercise can help us decrease visceral fat. And then we also, there's evidence to show that exercise can decrease the fat buildup in the liver too. And then, so then this should connect directly to exercise can improve in liver insulin sensitivity, right? So then this leads to the back to how it should be. Whereas when we release insulin, when we eat a meal, that insulin goes to the liver and tells the liver, stop releasing glucose, we've got enough, right? And so that's what it means by the proper inhibition of glucose release with insulin. Okay, there's a couple lines of evidence to say why HIIT might be more effective for visceral fat reduction than just regular exercise or lower intensity exercise. And those lines of evidence are here. We see that when they look at a visceral fat cell versus a subcutaneous fat cell, there's actually a much higher percentage or much higher density of epinephrine receptors on visceral fat cells than there are on subcutaneous fat cells. Okay, and so epinephrine levels are going to be higher in the higher the intensity of exercise you're doing, right? Because you got more sympathetic nervous system activity, and the effect of epinephrine binding to a fat cell is for it to break down the fat that it has in it and release it, right? And so that's kind of part of the idea, right? We'll come back to that one in a second. So part of the idea that why researchers think that high intensity exercise should be better for visceral fat reduction because of this difference in epinephrine receptors. Okay, and then secondly, the other part for fat burning and high intensity exercise is that the higher intensity of exercise you do, the more of your glycogen you drain in your muscle. And so that means after you're done exercising, all the glucose in your blood is going to go to replenishing that glycogen instead of being burnt. So what that means is instead of burning carbs during that post-exercise period, you're burning fat because the glucose you do have in your blood is going to replenishing that glycogen. And so there's some evidence to show that higher intensity exercise will lead to longer post-exercise fat burning during that epoch period that we talked about before. So that's kind of theoretical stuff. And some studies have shown those things. But when it comes to like a long-term study that compared HIIT to something else to see if it actually decreases fat better, we don't really have that yet. We don't really have evidence that HIIT is actually better for fat reduction. But there's some, possible physiological mechanisms here that could make sense, but we just don't have the long-term randomized control trials to actually prove that yet. Okay, so that's the liver. Exercise also has been shown to improve beta cell function. So again, if you're doing your concept map on this one, then you want to hit all three of these areas, right? You want to hit the skeletal muscle, glucose disposal, the liver, and the pancreas. Okay, both the pathophysiology of those and the effects of exercise on those. Okay, beta cell function is really hard to measure in humans because the gold standard way to measure beta cell function is to actually pull the pancreas out and measure what's called beta cell volume, which is just total volume of your beta cells. So obviously somebody can't live without their pancreas. And so it's not something we do on humans, right? But they do these studies on rats, and aerobic exercise trained rats have somewhere around 40 to 50% more beta cell volume than rats that are sedentary. And so we see, so within that beta cell mass, we also see increased production and storage of insulin. Okay, so they do other studies in humans where they have other ways to measure beta cell function. And what we see in those studies is after about 2 to 3 months of aerobic exercise in type 2 diabetics, we do see an increase in the ability of the pancreas to release insulin, but only in diabetics that can still release insulin. Okay, and that's something I didn't mention so far, but very advanced type 2 diabetics end up being just like type 1 diabetics. Their pancreas doesn't work at all anymore. And so once diabetics get to that point, it doesn't look like exercise actually fixes that at all. Most of the studies have shown once they get to that point of no return where they have to take insulin injections, just like a type 1 diabetic, exercise doesn't seem to improve the pancreas part. Exercise will still improve the skeletal muscle part, and it'll improve the liver part, hopefully, but probably doesn't get your pancreas going again if it's completely not working. So, yeah. Okay, and then this is just a meta-analysis on the visceral fat stuff that I was kind of mentioning. This is a meta-analysis where, they take all these different studies that have been done on visceral fat reduction and exercise, and they split these up into low intensity exercise, moderate intensity exercise versus high intensity exercise. Now these were not HIIT studies. Those are just that high intensity meant like vigorous exercise, like above 76% of max heart rate, something like that, but not HIIT. Right. And so with these meta-analyses, anything landing on the left side of this line means that the study showed a decrease in visceral fat. Right. And so then these down here are kind of the overall, when you put all the studies together, what happens. And so you definitely see there's a reduction in visceral fat with exercise training. But when you compare high intensity to moderate intensity, seems to be about the same in this group, right? Even with low intensity, maybe a little bit less powerful, but again, these aren't HIIT. These are just vigorous exercise. So there might be something different about HIIT, but that is kind of what we have so far. It does. Okay. Questions on any of that? All right. Well, let's take a second, and I want you guys to kind of recap with your team what we just talked about. So plug in the way exercise changes each of these. Okay. So what does exercise do to each of these factors? Kind of some brief on how it does it, and we'll come back together in a few minutes. Go ahead. So talk through that with the people on your team.
No, this is just like takes you to the body. So,
Wait, exam 2 is next, right?
yeah.
This is the last.
So, yeah,
This is the last material for exam 2.
for the exam, yeah. Uh-huh.
Okay.
Dr. Wu.
Yeah.
For
Uh-huh.
pathology of illness.
Yeah.
He's awesome.
Yeah, you
Yeah.
enjoying that?
Oh, yeah, for
Nice.
sure.
Yeah.
It's definitely a lot. It's like pretty dense, but
Uh-huh.
it's interesting.
Yeah.
And it's
he's-
cool because he has a lot of like first-hand experience like, in the.
Totally,
in the
like right before he comes over, right?
Yeah, yeah, literally, he
totally.
comes in, like,
Yeah, the
comes over in the
scrubs, right?
scrubs,
Yeah.
it's like-
Oh, that's pretty awesome. Yeah, I love that he's teaching that class.
I never heard of him before.
Yeah,
What class?
Pathology of illness.
It's a good class with him. It's really dense and difficult sometimes, but like he'll make a case study and he'll be like, oh yeah, I have this case. I'm like, this is what
Yeah,
happened.
no, it's cool. Like, your personal experience.
Yeah.
Like you hear like the textbook stuff, and then he's like, okay, but in reality, this is like that.
Yeah, that's awesome. All right, guys, let's come back together here. And yeah, couple, we're not leaving yet, Betsy, almost. Couple things here. So I can just kind of run through some bullet points here of kind of the basics here. With exercise, we see an increase in beta cell function, right? Which probably means an increase in insulin production and increase in insulin release. Right, with our liver, we see decreased hepatic glucose production, right? So less glucose released from the liver, and this probably happens due to, so we call it just increased insulin sensitivity. Right, the liver starts responding to insulin like it's supposed to, right? And this is definitely connected to visceral fat reduction and hepatic fat reduction. And these visceral fat is also connected to the pancreatic one for sure. And then on the skeletal muscle glucose side, right, we have the AMP kinase mechanism as well as the calmodulin mechanism. Both of these can acutely lead to increased GLUT4. So that can be acute, right? But then chronically, we can also increase GLUT4 production. Right, the acute one is just like activating the GLUT4 that's already there to go to the surface of the cells. But then the chronic one is actually causes your cells to make more GLUT4, so there's more available there next time insulin comes or next time exercise comes and tells the cell to put the GLUT4 on the surface. Okay, and then these also activate PGC1 alpha. I don't know if I can draw the little ichthyes thing. I don't think I can. Yeah, PGC1 alpha. And then that, I'll go down here, leads to increased mitochondrial health, pretty much. And then increase in our oxidative fibers. Oxidative. All right, so we get some fiber type transformation towards those more oxidative ones, and we get more powerful mitochondria in our cells. And both those things are going to call for more blood because those oxidative fibers need more blood. And then when the blood is being delivering the oxygen, we also can pull out more glucose from that blood to help us lower glucose levels. Questions on any of that or any of what I wrote there? Okay. I said I would walk you through a little bit of kind of the train of thought for the atherosclerosis one and exercise. Still happy to do that in the last 5 minutes, but if you guys are tired and ready for spring break, we don't have to do that either. But who wants to go through that a little bit? Okay, unanimous. That was the feel. That was the sense I was getting, so I wanted to check. Yeah. All right. Yeah. Okay. Well, yeah. Have a wonderful spring break, you guys. Enjoy it. Hope you get some rest. Don't forget about the gallery walks that you'll have to do when you get here on Monday. But have a good little bit of rest time, hopefully.